Hi class. In chapter 2, we use the tangent and the velocity problems to introduce the derivative, which is the central idea of differential calculus. Um, for chapter 5, we start with the area and the distance problems and use them to formulate the idea of a definite integral, which is the basic concept of integral calculus. And in chapter 6, we're going to use the integral to solve some application problems like volumes, length of the curves, population predictions, and so on. So there is a connection between integral calculus and differential calculus. So we begin this chapter with the area. Now let's talk about the area, the area of regions with straight lines. For example, the rectangle. We all know that the rectangle, the area is going to be length times width. The area of a triangle is half, base times height. So these are very simple because we have the straight lines, right? So if I have some regions like this, then I just get the area by getting the area of this triangle A1 plus A2 plus A3. However, it's not so easy to find area of a region with curved size. So for example, if I want to find the area under the curve right here, it's gonna be challenging, right? Therefore, let's take a look at number 1. We want to use the rectangles to estimate the area under the parabola. So you see that right here we have a parabola y equals x squared from 0 to 1. So these are the regions. So I want to estimate the area right here, this area, and I want to use the rectangle. So I have S1, S2, S3, and S4. Now, so we have 4 strips. You see right here, I have the rectangle. I have the rectangle. So we create 4 rectangles. The height of each rectangle is going to be x squared. The base right here you see is 1/4. From 1/4 to 1/2, that's 1/4, right? The base and the width is 1/4. Now we're gonna use the right endpoint for the height. So that's why I denoted R4. So you see what is the area of rectangle? We have width times height, right? Width times length, but in this case, it's going to be the height. So what I have is for S1, the base is 1/4, which is the width, and then the height is 1/4 square, x squared, and so on. So we have 1, 2, 3, and 4. That's because I'm using the right endpoints here. So I have the right, the right, the right, and the right. Now, we're gonna go the other way around. So you see that this is overestimated, right? Now right here, I'm gonna use the left endpoint. So I'm starting right here. And then we have this one, this one, this one, and then this one. So if I have those, if I consider those endpoint, then L4, L stand for left, I'm gonna get these areas. So when we add them up, you see right here we have 0.468, right here we have 0.218. So what's the area of S? You see the area of S is gonna be in the middle, so it's bounded by L4 and R4. All right, so I want to make a remark here. If we compute the sum of the area of the smaller triangles, we will obtain better lower and upper estimates for A. So instead of dividing into 4 strips, I can divide into 8, 100, 1,000, and that's gonna bring the left and the right closer and closer to the actual area. All right, you see right here at sample 2, we want to find, for the regions in the sample 1, we want to show the sum of the area of the upper approximating rectangles approaches 1/3. So pretty much I'm looking for the limit, right? So for Rn, we defined it as the sum of the area of the n rectangle. The width, which is the base right here, is going to be 1 over n for every rectangle. The height is going to be right here. So that's x squared at 1 over n, 2 over n, 3 over n, and so on, n over n, which is 1. And then I have Rn. So this is considered n rectangles. So that's why I have all the way to n over n squared here. Now if you do some algebra, we factor out 1 over n, and then I factor out 1 over n squared. I ended up with 1 squared plus 2 squared plus so on to n squared, right? And then I multiply these two. That's how I got 1 over n cubed. And that. Now, I'm going to use a formula right here. And this formula is for 1 squared plus 2 squared plus 3 squared plus all the way to n squared. It's going to be that one. Okay. So for Rn, right here, I just pretty much take this and substitute with the formula. I cancel out n, then I take the limit. You know how to take limit. So you see it goes to 0 when n approaches to infinity. So we have 1, 6 times 1 times 2. Therefore, it's 1/3. Okay. So that's example 2. Now moving on to definition of area. So you see right here the area A of the region S that lies under the graph of the continuous function. F is the limit of the sum of the areas of approximating rectangles. So I'm taking Rn right here, and then that's just the limit, taking the limit. Okay. So you see right here I have x1 star, x2 star, x3 star. These are the sample points, not the endpoints. And don't forget, just like what we did earlier for the lower and the upper limit, area is going to be right in the middle, left and right, lower, upper. We form lower and upper sum by choosing the sample points so that the function fxi star is the minimum and the maximum values of f on the I subinterval. And then 4, we have something called a delta x. The delta x is defined by b minus a over n, which is the width of each of the n strip. Okay, and then I'm just calculating x1, x2, x3. x0 is a plus delta x. So x2 has to be a plus 2 delta x and so on. Okay. So let's try one example. So we have the function e to the negative x, and then is bounded by 0 and 2. X equals 0, x equals 2. For part A, they want you to use the right endpoints, and then we have to find the expression for A as the limit. I don't want you to do evaluate. Now for part B, we want to estimate the area by taking the sample point to be the midpoint this time and using 4 subinterval. Okay, and then 10 subinterval. So first, what do? We recognize that A is going to be 0, B is going to be 2. The width of a subinterval is going to be delta x, which is what? B minus A over n. So I use it. So it's 2 over n. x1, you see right here, the first term is 0 plus 2n. x2, 0 plus 2 times 2 over n, which is 4n. x3, I'm doing the same manner. So I know that in general, xi is going to be 2i over n. So xn is going to be 2n over n, which is 2. Right? And then using the right endpoint, this is what we're going to get. I plug it in, right? And then from here, we want to plug it in for x1, which is negative 2 over n. Delta x is 2 over n. And then I plug it in for negative x2. I plug it in for negative xn, so on, right? And then from there, we are taking the limit at as n approaches to infinity. So you can see right here, I can just factor out 2n. I have e inside, the e function inside. So taking the limit, I'm going to end up with the series, right? This is a summation, so which is a series, and that's a function from 1 to n. Okay, now that's the general form, right? We're gonna use n equals 4, so we have 4 subinterval. The same thing, instead of n, this time I have 4. So I have 2 minus 0 divided by 4, which is a half. Since I have 4 subinterval, these are the points, right? Now, from here, because the question asks you to use the midpoint, so I'm using the midpoint of this one. I'm using the midpoint of this one, the midpoint, the midpoint. And then I plug it in, right? So the function f of 0.25, I'm using the midpoint delta x, and so on. What is f of 0.25? Is e to the negative 0.25. And then 0.5, that's delta x. And then moving on, moving on, moving on, 4 subinterval. Once again, we factor out 0.5. We calculate it. You can use a calculator for it. And we got this number right here. If I use n equals 10, so the delta x is going to be 0.2 this time. And then I have 10 subinterval. I'm using the same idea. I'm using midpoint here. Okay. And then I plug it in just like because we have the general one from part A. So I just use it to plug it in right here. And then once again, I'm using the calculator to get this one. You can see that M10, of course, it has to be better estimate than M4. And of course, if you do 100 subintervals, it's going to be better. 1,000 subinterval is going to be better. All right. Moving on to the distant problem, just like chapter 2. So the distant problem, we have distant equals velocity times time. Now, you see right here, I have the example. So we have the cars broken down. We want to estimate the distance driven over a 30-second time interval. So right here, that's a table. Okay, so I'm taking the readings every 5 seconds. So this is 0 second, 5 second, 10 second, 15, 20, 25, 30 seconds, and so on. And then these are the numbers for velocity. Now, the distance is the limit, you see right here, as n approaches to infinity of the summation of f of ti minus 1 delta t. T is time. Okay, so before I proceed the problems, I have to convert 1 miles to hours to second because we're dealing with the third 30-second interval, so I have to convert it. Huh? All right, so from here, from this table, I got to this table because it's from feet to second. Now, assume that during the first 5 seconds, the velocity is constant. Okay. Then I can just simply take velocity times time equals to 125. Second time interval, same thing. I take the velocity times 5, 155. And then we keep doing that. We keep doing that for the whole thing so we can estimate the distance. And the distance, the estimate is 1130 feet. We could estimate by using the velocity at the end of each time period instead of the beginning. So instead of starting at 25, I can start at 31 right here. And you see that the estimate is going to change. Okay. Now, if we want better estimate, of course, instead of taking the velocity after 5 seconds, we could take it after 2 seconds or even 1 second. That's going to be better if we want a better estimate.